4 light years away, in the closest star system to our own sun, something appeared in a James Webb Space Telescope image that nobody had ever seen before. A faint point of infrared light, 10,000 times dimmer than the star it orbited, sitting at approximately twice the distance from its star that Earth sits from the sun, in the zone where liquid water can exist, in the star system that humanity has dreamed about reaching for generations. Astronomers who saw the August 2024 data described it as popping out so clearly that even the deep skepticism that every planet hunter trains into themselves as a professional reflex could not suppress the immediate recognition that something real was sitting in that image. And then they looked again, in February 2025, in April 2025, and it was gone. The planet that had appeared so clearly, so unambiguously, so startlingly in the first Webb observation of Alpha Centauri, A, had vanished. Not faded, not blurred, gone. And the team of scientists left staring at the empty space where a world had been found themselves, saying something that has never been said before in the history of exoplanet science. We are faced with the case of a disappearing planet. Alpha Centauri has occupied a singular position in the human imagination for as long as we have known what it is. It is the closest stellar system to our own sun, a triple star system sitting just 4.2 light years away in the southern constellation of Centaurus, visible as the third brightest star in the night sky to anyone standing in Earth's southern hemisphere. The system contains 2 sun-like stars, Alpha Centauri A and Alpha Centauri B, orbiting each other with a period of about 80 years at separations, ranging from 11 to 36 astronomical units, and a third much fainter red dwarf companion called Proxima Centauri, that orbits the pair at a distance of about 13,000 astronomical units and holds the specific distinction of being the single closest star to our solar system at 4.24 light years. Proxima Centauri is already known to host at least 3 planets, including Proxima b, a roughly Earth-mass world sitting in the habitable zone of its star that has been the subject of intense scientific attention since its discovery in 2016. But Proxima Centauri is a red dwarf, a small, dim, frequently flaring star that subjects anything orbiting in its habitable zone to radiation levels and stellar activity that make the prospects for life as we know it deeply uncertain. Alpha Centauri A is different. Alpha Centauri A is almost a twin of our own sun, with 99% of the sun's luminosity, a similar surface temperature, a similar age of approximately 5 billion years, and a similar chemical composition. It is, by every measure available to stellar astronomy, the most sun-like star within any distance that makes a planetary system there feel personally relevant to the human story. If Alpha Centauri A has a planet in its habitable zone, that planet orbits a star so similar to our own that every question about whether other solar systems like ours exist in the universe is answered immediately and definitively by the nearest stellar neighbor we have. The search for planets around Alpha Centauri A and B has been ongoing for decades and has produced a long series of detections that did not survive scrutiny. A 2012 announcement of an Earth-mass planet orbiting Alpha Centauri B, published in Nature and greeted with enormous excitement, was subsequently reanalyzed, and the planetary signal was attributed to an artifact of the data analysis method rather than a real world. The detection dissolved. Other candidate signals over the years met similar fates. By the time Webb turned its mirror toward the system in 2024, the history of Alpha Centauri planet hunting was a chronicle of hopes raised and methodically deflated, of signals that looked real long enough to generate excitement before being explained away. The field had learned to be very careful with this particular star system. The reason Webb's August 2024 observation represented something qualitatively different from those previous detections is the nature of the technique it used. All of the previous Alpha Centauri planet candidates had been detected through indirect methods, the radial velocity technique that detects the gravitational wobble a planet induces in its star, or the analysis of subtle patterns in the stellar light that might indicate the presence of orbiting companions. These methods are powerful, but they produce signals that can be mimicked by instrumental artifacts, stellar activity, or data processing choices, and they have repeatedly fooled researchers into announcing detections that subsequently could not be confirmed. What Webb did in August 2024 was direct imaging. It took a picture, an actual photograph of the space around Alpha Centauri A, with the star's blinding light blocked by a coronagraphic mask, and in that photograph a faint blob of infrared light appeared at a separation from the star corresponding to approximately twice the Earth-Sun distance. The engineering challenge involved in producing that photograph is one of the most demanding things the James Webb Space Telescope has ever been asked to do, and the fact that it succeeded is itself a testament to what this instrument is capable of. Alpha Centauri is one of the brightest stars in the sky. and its companion Alpha Centauri b sits close enough in the sky that its light contaminates the region around Alpha Centauri a, making the background against which a faint planetary signal must be detected extraordinarily difficult to clean up. The team, led by Aniket Sanghi, a doctoral student at Caltech, and Charles Beichmann of NASA's Jet Propulsion Laboratory, used Webb's mid-infrared instrument with its coronagraphic mask to block Alpha Centauri A's light, then applied sophisticated image processing algorithms to subtract the residual contribution from both stars, peeling away layer after layer of contaminating light until the underlying image was clean enough to detect sources 10,000 times fainter than the star itself. The team was able to subtract out the light from both stars to reveal an object over 10,000 times fainter than Alpha Centauri A, separated from the star by about 2 times the distance between the Sun and Earth. When the cleaned image revealed a clear, unambiguous point source at that location, the team's first response was not celebration. It was the systematic attempt to explain the detection away. This is what rigorous science looks like when the stakes are high enough that being wrong is worse than being cautious. They considered every alternative explanation available. Could it be a background galaxy sitting far behind the Alpha Centauri system and simply appearing to be in the same location? The color and brightness of the source were inconsistent with background galaxy profiles. Could it be a foreground asteroid in our own solar system, passing through the field of view during the observation? The motion of known asteroids was modeled and ruled out. Could it be an artifact of Webb's optics, a ghost image created by the instrument itself rather than a real object in the sky? The team's careful analysis of the known diffraction and scattering patterns of Webb's mirrors and support structures found no instrumental artifact that could produce a source at that specific location with that specific brightness. Several rounds of meticulously planned observations by Webb, careful analysis by the research team, and extensive computer modeling helped determine that the source seen in Webb's image is likely to be a planet, and not a background object like a galaxy, foreground object, a passing asteroid, or other detector or image artifact. The detection also connected to an earlier observation that had been sitting in the literature since 2019 without achieving the status of a confirmed detection. The team incorporated more data by re-examining a puzzling 2019 observation of Alpha Centauri A from a ground-based telescope that, while constituting the first hint of a directly imaged planet there, never quite solidified into a confirmed world. The 2019 candidate from the Very Large Telescope in Chile and the 2024 candidate from Webb were not in the same position relative to the star, but that was expected. A planet orbiting Alpha Centauri A would be moving through its orbit between 2019 and 2024, appearing at different positions in the sky as it went. When the team modeled whether a planet on a physically plausible orbit around Alpha Centauri A could appear at the 2019 position in that year and the 2024 position 5 years later, the answer was yes. The two detections were consistent with the same planet observed at 2 different points in its orbit, 5 years apart. And then February 2025 arrived. Webb looked again, with the same instrument, the same technique, the same careful image processing. Nothing. The source that had appeared so clearly in August 2024 was not there. The team looked a second time in April 2025. Still nothing. The research team needed more data to come to a firm conclusion. However, additional observations of the system in February 2025 and April 2025, using director's discretionary time, did not reveal any objects like the one identified in August 2024. The temptation at this point was to conclude that the August 2024 detection had been a false alarm after all, that whatever appeared in that image was not a planet, and that the follow-up non-detections had correctly identified it as an artifact or a background object that had moved out of the field of view. But the team resisted that conclusion and instead did what the data actually demanded. They modeled it. They ran millions of computer simulations of potential planetary orbits around Alpha Centauri A, testing which orbits were physically stable, given the gravitational influence of Alpha Centauri B. And for each stable orbit, they asked whether a planet on that orbit would have been detectable in August 2024 and undetectable in February and April 2025. Researchers say a non-detection in the second and third round of observations with Webb is not surprising. They found that in half of the possible orbits simulated, the planet moved too close to the star and would not have been visible to Webb in both February and April 2025. The disappearing planet turned out to have a straightforward orbital explanation. A planet on an elliptical orbit around Alpha Centauri A, varying between 1 and 2 times the Earth-Sun distance from its star, would be detectable by Webb only when it was at the outer part of its orbit, far enough from the star's glare to appear as a distinct point source in the cleaned image. When the planet is at the inner part of its orbit, close to the star, it disappears into the coronagraphic mask and the residual starlight, becoming invisible to the instrument regardless of how carefully the images are processed. In August 2024, the planet was at or near the outer part of its orbit. In February and April 2025, it had moved inward, into the zone where it could not be detected. This is not a failure of the detection, it is a prediction, a specific, testable, falsifiable prediction about where the planet should be in its orbit and when it should again become visible to Webb. The model comes with a strict prediction that the planet should again be visible in 2026 or 2027. These follow-up observations will be key for confirming this planet. August 2026 is identified as the next good observing window, when the orbital models predict the planet should have moved back to the outer part of its orbit and become detectable again against the background of cleaned Alpha Centauri imagery. The confirmation or refutation of the planet candidate is therefore not a matter of indefinite uncertainty. It has a specific timescale. Webb is almost certainly going to look again. And when it does, the result will be definitive in a way that single epoch detections never can be. The characteristics of the planet candidate that the Webb observations and orbital modeling have outlined are simultaneously exciting and sobering in equal measure. The possible Saturn mass world may travel between 1 and 2 times the distance from its star that Earth does from the Sun. The planet appears to lie in the habitable zone, though its gas giant nature makes it unlikely to host life, a Saturn mass gas giant in the habitable zone of the nearest Sun-like star. Not a rocky terrestrial world where liquid water might pool on a surface and chemistry might reach toward biology. A gas giant with no solid surface, with crushing atmospheric pressures, with conditions utterly hostile to any life form we have ever encountered or can currently conceive of. The habitable zone location is significant, not because the planet itself might host life, but because of what it implies about the system architecture around Alpha Centauri A. In our own solar system, the gas giants Jupiter and Saturn play a critical role in shaping the conditions for life on Earth. Jupiter's enormous gravitational influence deflects many of the comets and asteroids that would otherwise bombard the inner solar system far more frequently than they do, potentially having allowed the relative stability that permitted complex life to develop on Earth over billions of years. A gas giant in the Alpha Centauri A system, if confirmed, implies a system with sufficient mass and structure to have potentially allowed rocky inner planets to form and survive in stable orbits. Its very existence in a system of 2 closely separated stars would challenge our understanding of how planets form, survive, and evolve in chaotic environments. The 2 closely separated stars. Part of that statement is the element that makes the Alpha Centauri A planet candidate most theoretically interesting beyond its sheer proximity. Alpha Centauri A and B orbit each other at separations ranging from 11 to 36 astronomical units, close enough that their mutual gravitational influence significantly perturbs the orbits of any planets trying to form and survive in the system. Planetary formation models have historically suggested that this gravitational chaos makes it difficult for stable planetary systems to form around either star in the binary. Finding a Saturn mass planet in a stable habitable zone orbit around Alpha Centauri A would not just confirm a planetary system at the nearest star. It would demonstrate that binary star systems, which constitute the majority of stellar systems in the galaxy, are far more hospitable to planet formation than the models have typically assumed. The implications for the overall abundance of planets in the galaxy, already known to be enormous from the Kepler mission data, would shift further upward. With this system being so close to us, any exoplanets found would offer our best opportunity to collect data on planetary systems other than our own. Kevin Wagner, an assistant research professor at the University of Arizona's Steward Observatory who was involved in the 2019 ground-based detection and the 2024 Webb observations, described the discovery as shaping up to be one of the most exciting results in astronomy of the decade. Charles Beichman of JPL summarized what confirmation would mean for the field with characteristic understatement. If confirmed, the potential planet seen in the Webb image of Alpha Centauri A would mark a new milestone for exoplanet imaging efforts. Of all the directly imaged planets, this would be the closest to its star seen so far. It is also the most similar in temperature and age to the giant planets in our solar system, and nearest to our home, Earth. Stanimir Mechev, Canada Research Chair in Extrasolar Planets at Western University in Ontario, said the signal is at the limit of what contrast enhancement techniques applied to JWST images can deliver. The authors go through a painstaking and believable analysis, but nonetheless, any direct image of an exoplanet, especially one with such potential significance, will require an independent confirmation. That independent confirmation is exactly what the August 2026 observing window is positioned to provide. Webb will look. The planet, if real, will be there. The planet, if it was a false alarm, will not. The universe will answer the question on its own schedule, which now appears to be measured in months rather than years. There's a quality to this particular discovery that sets it apart from the thousands of other exoplanet detections that have accumulated over the past 3 decades of systematic planet hunting. The other planets are out there, They are real. They are scientifically important. But they are also remote in a way that makes them feel, despite everything we know about them, like features of an abstract universe rather than neighbors. 4 light years is the closest anything gets. Alpha Centauri is the one stellar system that people who think seriously about humanity's long-term future in the cosmos return to again and again as the place the species might one day reach. Proposed spacecraft concepts, laser-propelled sail designs, generation ship architectures, they all eventually converge on that same destination. Not because 4 light years is easy to cross. It is not. It is almost incomprehensibly far by the standards of any technology currently available, but it is the closest thing there is, the nearest neighbor. The first step beyond our own system, if a step is ever taken. The faint blob of infrared light that appeared in a Webb image in August 2024, 10,000 times dimmer than the star it orbited, sitting in the habitable zone of the most sun-like star within any personally relevant distance, then vanishing from the next 2 observations and leaving a team of scientists with orbital models and a waiting window in 2026 to find it again, is the most compelling single data point in the history of the search for planets around our nearest stellar neighbors. Not confirmed, not refuted. Orbiting through the period of invisibility that the models predicted, moving on its elliptical path around a star that is almost exactly like our own, in a system that humanity has been staring at for as long as we have had telescopes pointed at the night sky. August 2026 is coming. Webb will look. And whatever it finds in the space around Alpha Centauri A, the next time it opens its infrared eye on the closest solar twin to our sun, will be one of the most consequential images ever taken by a human-built instrument. Either a confirmation that changes everything, or a silence that resets the search and sends the best planet hunters in the world back to the data with harder questions. Either way, the answer is almost here.